Wonderful. Well, thank you so much for the invitation to join you all here today. I'm so excited to be with you to celebrate this occasion. It's my pleasure to welcome you to the George R. Pack Student Awards Symposium, an event that highlights the outstanding achievements of our graduate students in the Department of Chemistry. As Dean of the College of Arts and Sciences, I'm honored to join you in celebrating the hard work, the dedication, and the research excellence demonstrated by our grad students. The College of Arts and Sciences has a long-standing commitment to fostering research, scholarship, and innovation. Across all disciplines, we take great pride in supporting the curiosity and dedication of our students and our faculty who are here today. Nowhere is this more evident than in the chemistry department. With nearly 60 students in your PhD and MS programs, this department continues to thrive as a hub of scientific inquiry and discovery. The awards presented today, particularly the prestigious George R. Pack Award for Most Outstanding Chemistry PhD Dissertation, serve as an important reminder of the impact of graduate education and the importance of recognizing excellence in research. This year, we are thrilled to congratulate Sachal Chopagan of the Grapper House Group, the recipient of the 2025 George R. Pack Award. Sachal's work exemplifies the spirit of perseverance, creativity, and scientific rigor that this award was designed to honor. And of course, sorry, Sachal. And I want to make sure that we acknowledge the George Pack, who brought us together today and did so much to grow and support this department. None of this would be possible without George R. Pack, whose contributions to this university and the chemistry department continue to inspire us. Dr. Pack joined the University of Louisville in 1998 as professor and chair of the chemistry department. To some of you, that probably seems like a really long time ago, but his vision and leadership led to the hiring of 19 faculty members and the conferral of 58 doctoral degrees during his tenure. That's so impressive. Evidence of his dedication to growing a robust graduate program. Beyond the department, he served as Associate Vice President of Research, ensuring that scientific advancement remained a priority across our institution. And today we're privileged to have members of the Pack family join us as we celebrate his legacy and the achievements of our students. Please join me in welcoming Dr. Pack's siblings, Patty Pack, Barbara Hauser, is it Hauser? Yes. And Thomas Pack, along with his sister-in-law, Jerry Pack. Your continued support of this award and our students means so much to us, and we are grateful for your presence here today. To all of our award recipients, I extend my heartfelt congratulations and thanks for the work that you've done. Your accomplishments reflect not only your individual dedication, but also the strength of our chemistry faculty and their commitment to both teaching and research. We look forward to seeing where your academic and professional journeys will take you. And I hope that you stay in touch and keep us abreast of all of your successes and accomplishments. Thank you again for joining us in this celebration. I'll now turn things over to Dr. Muriel Maurer, Professor and Director of Graduate Studies, who will share more information about the remarkable legacy of Dr. George Pack.
Thank you very much for Dean Horn for the introductions. I'm Muriel Maurer. And again, I'd like to welcome everyone here to the George R. Peck Symposium that we have here. It's a great day to celebrate this event and honor our graduate students and the awards. I want to point out, I think this is the 10th anniversary of it, and I think one year there were 2 people who won, so Sheila is now the 11th person to receive this particular award. In addition, again, recognizing the different members of the Peck family. It's always great to have you come and further participate. Also would like to thank the chair of the department, Frank Zamborini, and also the vice chair, Lee Thompson, for your contributions. I'd also like to recognize James Kruger, who is our new departmental coordinator, and all the efforts that he has to help us to put this particular event together. I also want to recognize Amanda, who plays multiple roles. She's our stockroom manager. She's a graduate student. She also has helped with the setup of the reception that we had for today. That we have. Okay, and I guess we have heard that George Peck, that he got his PhD from the State University of New York in Buffalo. He then later went on to do postdoctoral work at University of Rochester, the New York University Medical School, and also at Stanford. And we saw how he began his career in 1978 at the University of Illinois College of Medicine. We want to think in terms of what his research focus was, and that was in the area of the biophysics of DNA. So he was very much interested in the roles that different ions played, sodium, potassium, calcium, magnesium, what they played with impact on DNA structure, the condensation effects, and also sort of structural transitions that took place. And he had an active computational research group that he had. As we heard, he came in 1998 to the department. He had a really strong dedication to the research and establishing this robust department. It's impressive to see the growth of the department. There are so many people who were still in the audience here who came during that time period that he was here. And then we were able to see the extent to which the graduate program has, expanded and grown since then. I think it's important to note that in addition to being the chair of the department, that he also was involved in teaching. He taught Chemistry 441. This is our one-semester physical chemistry course that's taught by students in the BA program. It's also taught by students who are getting a minor. And then importantly, we have the new biochemistry degree program, BS Biochemistry program, and they will be taking that same course as part of their degree program also. We can think about other sort of commitments that George was involved in terms of extensive amount of curriculum development that took place, and we ourselves as faculty are thinking, how are we going to continue to do some of those types of things also. We can also think back to some kind of pioneering programs that he was involved in. We have things like the GEMS program, which was an NSF-funded program that brought this was done by Dr. Christy Rich, which brought graduate students together with public school teachers. That later led on to another grant, another NSF grant, that is the PRIMES program, that provided then training for undergraduates to serve as teaching assistants in the group. And it's kind of nice as we think of the progression that we also have now the Division of Chemical Education that takes place, allowing us now to have graduate students also have more opportunities to get PhDs and expand in that particular area. I guess we can also think about the number of graduate students we have, the increases that we have in those graduate students, and I've been very pleased to see how that has progressed over the years. And we want to thank to those students who have gone on to postdoc positions, government labs, academia, and so forth. We have ones going industrial positions, and we even have examples like Sochil, someone who then goes on and is involved in their own startup company. So that's great to see the variety of careers that people have had. I think another thing to kind of think about might be instrumentation that's in the labs. From my own experience, as I came in 1997, so in 1999 as an assistant professor, Dr. Peck was always very much involved in promoting the activities of assistant professors, and being assured what could best happen with them, what could allow them to succeed along the way. In my particular case, I had interest in some NMR mass spectrometry cases. We were quite fortunate at that time to be able to have Kentucky State bond money that became available. And I then went first with Arno Spatola to Boston to look at a series of mass spectrometers. Then I went with Neil Stolovich, the NMR manager, back to Boston to see NMR spectrometers. We had to do a lot of looking at the calculations. And I must say, as an assistant professor, as the order was placed, I thought, gosh, I hope we made the right decision. It was a lot of money. Those instruments lasted quite a bit of time. Of course, over the years, one hopes we can get more improvements and more instrumentation into the department. I think the other thing to think about also is that he was that Associate Vice President of Research, that he did that from 2007. At the same time he was that, he was also still continuing on as the chair of the department, and then moved on full-time to that Associate Vice President of Research position until his passing in 2013. I think other things to think about is we're all gathered here together for the seminar series. This is where we also have our departmental seminars. George always attended those particular events. He was typically sort of towards the front. He asked a lot of questions, and from there, that was always fun to see where those would go to. And then afterwards, he would sort of encourage further discussions to take place. I think in addition to the sciences and the education, I think we know that he had strong interest in the sports, both in football, I think also in the basketball games to take place. But he wasn't just, science and sports. We know he had other interests, and he had, season tickets to the Louisville Opera. So that's here. Well, I think today we're here to honor the graduate students with a series of awards. We'll announce the Dorothy Gibson Award, and then our capstone will be the George Pack Outstanding Dissertation Award for Sir Shiel. You'll notice in your program here is that you have a bow tie, and a little bow tie. That's sort of a new feature for our particular program. So we know that George always frequently wore a suit. Always interesting to see the tie that he wore, and this provides us kind of a little extra honor for that. And then you'll see that the little bird has a bow tie also. So, all right. Well, I think we can then move on to the next parts of the program. Okay. Right, I think we went. Let's see. I think that there's supposed to be some photographs taken. Okay. All right. All right. So our first award that we will give out is for the Best Laboratory and Graduate Teaching Assistant. All right. And that award goes to Sanji Kurki. And then our next award goes to the Best Recitation Graduate Teaching Assistant, and that award is going to go to Regina Gasparetto. All right. Congratulations. Yeah. Okay, we move on to the next award. This is an award that's given to the first-year student. This is the most auspicious first-year student, and that person is Shane Pascal. Congratulations. The next award we have is this is the award for character and endeavor that takes place, and this year we are going to be recognizing Amandeep Kaur for that award. Congratulations. What we're doing now is this is for the Dorothy Gibson Fellowship Award. This is one in honor of, she was actually the first female faculty member here at the University of Louisville, Dorothy Gibson. And this is for a student who has just completed the fourth year and is moving on. So And this year's winner is Nurian Bakara. Yeah. All right, congratulations. Now we were at our final capstone award that we have, and that is for the George R. Pack Award for the outstanding PhD dissertation. And our winner for this year is Shashil Chapagan, who comes from Craig Grapper Circle
We'll do one with her before you want to get but then we'll have the family.
Alrighty, I'll shake your hands a little.
I will go wherever you tell me.
Everybody out of that light.
Oh, well.
There we go. Okay, everybody, big smile right here. And one more. Okay. All right. Thank you.
So now I think we're moving on to the, let's have the research mentor, Dr. Grapperhaus, Craig Grapperhaus, do an introduction for Shashil, for George Pack honoree for this year, or 2024.
Before introducing Shashil and talking about Shashil, I have to talk about George. He's the reason that we're here today. I was early in that group of the many faculty that George hired here at U of L, and it's really hard to think about any part of my professional career that wasn't touched and influenced by George. I worked with him first as an assistant professor. He was a great mentor as I was getting my research program and teaching started. But then I also had the opportunity to serve under him as vice chair and learn about leadership from him. And what I really noticed with George is that if you're passionate about what you're doing, it can be the science, it can be the leadership, it's what you put your heart into and what you put the dedication into, that you can have a very rewarding and successful career. That we can think about our careers, and that's one of the beauties of being in academia, is you don't have to do just one thing forever. You can be a researcher like George was, and then move into a chair position and build a department, and then he moved into the associate vice president role. And you could just tell from interacting with him that every role that he was in, he was just enjoying it so much and putting so much effort into it. And I really took a lot of inspiration from George in my own career as I've kind of changed and done different leadership activities in addition to my research. In terms of research, he gave me a piece of advice early on, and he said, work on important problems. which sounds really like simple advice, but in academia we work on problems that we think are important, right? But maybe not everybody agrees. But he said, work on important problems because unimportant problems are just as difficult to solve, but nobody cares. and so it took me about 18 or 19 years to finally start working on an important problem. and that is the project that Sashil worked on. I'm up here as Sashil's mentor, but I need to acknowledge Thad Druffel there in the second row from the Kahn Center for Engineering. Thad was Sashil's co-mentor, but more important than that, I would have never gotten into this area of research without Thad. And I first got involved in this project at a Kahn Center meeting where when requests for proposals come out, the Kahn Center faculty would get together and kind of brainstorm about, can we put together a proposal that's going to be competitive? And Thad had a really interesting project, and he needed a chemist, specifically an inorganic chemist, to work on it. It was an area I had never been in, never would have considered going into, but I said, this is an important problem. Yes, we can help. Sashil and Peter Armstrong were two very brave first-year students who started on this project where they really had to teach me about the chemistry and the science. And so both Sashil and Peter did phenomenal jobs during their PhD career of defining the chemical aspects of this very application-driven project that we were working on. Sashil came to us from Middle Tennessee State with his master's degree, joined here, started on the project, and he'll tell you about the chemistry, I'm sure. But he had the opportunity through this project to also spend about 5 or 6 months at the National Renewable Energy Lab in Golden, Colorado, really getting experience with world leaders in the field of photovoltaics, renewable energies, and the perovskite solar cells he's working on. The timing got all weird with COVID, but he persevered through that. The advances that he's going to talk about, I would love to take credit for them, but these are Sashil's advances. Peter has advances that were complementary, but it was really a team effort. And from that team effort, Sashil and Peter and Blake Martin, who was an engineering student with Dr. Druffel, took the technology that was developed on Sashil's project and actually turned it into a company, which is located right here in Louisville. I cannot take any credit for them being entrepreneurs. This is something that they did. Thad gave them wonderful advice as an entrepreneur himself. I'm not an entrepreneur, I'm along for the chemistry and the science, and just impressed with the work that this group of students has done, that Sashil has done with them. Sashil was also a great member of the group. You never had to guess what Sashil was thinking. He came to group meetings, he was prepared, he had his ideas, and he had done his homework and he was ready to defend his ideas. He was a fantastic student and a fantastic colleague for the other students in the group. He was also really the life of the party at a lot of our group gatherings, and I won't embarrass him with any stories from those, but he still gets invited back even after graduation. When we have group parties, Sashil is always on the guest list and is still a life of the party. So I think I've exhausted my time, and so I just want to say, Sashil, congratulations. I'm so proud of you and the work that you've done, the company that you guys are building and where you're going with this. And you truly deserve this award, and I'm happy to have had the chance to be your mentor. And congratulations, and we look forward to hearing your talk.
At first, Dr. Jabrao, thank you very much for the kind introduction. Actually, whatever I completed here, this whole work is due to the help of my advisor and whole chemistry department, and also Conn Center for Renewable Energy Research, and I got great platform there under Dr. Thad and other people, seniors, and also I learned a lot of things from National Lab. At first, good afternoon, everybody, and thank you very much for joining me today. I would like to express my deep gratitude to the chemistry department for selecting me as the recipient of George Pack Award this year. And it's truly an honor to be here. I'd also like to extend my sincere welcome to the Pack family and distinguished guests. And thank you everyone for your support and invitation. Now I want to go to my presentation. Here I try to make this presentation as simple as possible, but still it contains a lot of technical word. The reason is like engineering, but I'll try to explain in a simple way that everybody can understand. And you can ask me question anytime. And here, the title, here I'll be talking about completely different type of solar cell technology. It is the perovskite solar cell. In perovskite solar cell, it has incredibly simple fabrication process. Just we can deposit different layer and we can make cell. And we can do such type of research in our lab. And it's not difficult like silicon. We don't need any sophisticated instrument. At least we need some basic instrument for the metal deposition. And a lot of lab, they do not have, but it's not expensive like silicon. And it can be done in most of the university. And I hope near future silicon will be predominant. And also silicon has, perovskite will be the predominant. Perovskite has another benefit. And there is pre-existing silicon solar cell, and we can stack perovskite solar cell on the silicon solar cell, and we can make a tandem device. This tandem might be the future of the solar cell. And to make simple, I divided my talk into different sections. And this is the background of my talk. And first, I'll talk about background as fundamental of solar cell, perovskite solar cell. After that, I'll go to formation of perovskite compatible tin oxide dispersion. And after that, I'll go to application of tin oxide and performance of tin oxide ETL. And after that, I'll go to perovskite photovoltaic and how does it work as a multi-junction device. And after that, performance of the tin oxide and multi-junction device. Perovskite photovoltaic, this is the youngest member, perhaps youngest member in solar cell technology. But however, it is youngest member, but it is very important. And if you look at this best research cell efficiency chart, this is the chart National Renewable Energy Lab published. And this chart, it shows the power conversion efficiency of different type of solar cell technology over time. And this is for the silicon, this is for the perovskite, and this is for the tandem. And if you look at it here, perovskite solar cell, it was invented 2008 and 9, but it was popular after 2014 or 15, and people started to do more research after 2014. And just above 10 years, the power conversion efficiency, the progress in power conversion efficiency is incredible, and it's already near to 27%. And this is the silicon solar cell, and which is market dominant, and still more than 90% of the solar cell and solar panel in market are silicon solar cell. If we compare perovskite with silicon, silicon took more than 30 years to achieve power conversion efficiency more than 26%. And if you look at here, after 2000, the progress in power conversion efficiency of the silicon-based solar cell is almost insignificant. And another aspect of perovskite-based photovoltaic is multi-junction device. This is the multi-junction device of perovskite and silicon. That means we can fabricate perovskite solar cell on the top of silicon solar cell in a very easier way by depositing different layers. And when we make tandem device, when we fabricate perovskite solar cell on the top of the silicon, we can improve in power conversion efficiency. And This is the power conversion efficiency of silicon. This is for the perovskite, and this is the combination of both cell, and it's already more than 34%. It is really incredible. If we talk about scalability, and another benefit of perovskite-based photovoltaic, it is solution processable, and we can mix precursors together, and we can deposit it, and we can make solar cell. It's a very, very simple. And due to solution processability, yeah, we can make large area perovskite solar cell using inexpensive deposition technique. Yeah, we can use simple sort die technique and spray coating technique and roll to roll, and we can replicate perovskite solar cell. It does not need any complicated process like silicon solar cell. That's why, due to high efficiency and easier fabrication process, and also compatibility with the multi-junction device with silicon, perovskite might be the future of solar cell. But let's see, time will show. The photoactive material, light absorbing material, the main component of perovskite solar cell is halide perovskite. Basically, perovskite is a wide group of wide range of chemical compound, which can be represented by very simple general formula ABX3, in which A are cation, B are cation, and those X are anions. This is an ideal unit cell structure of perovskite. This is an ideal unit cell, and here those A side cation are present inside the unit cell at the center of the unit cell. Those B side cation, they are present inside the corner sharing octahedra, and X anions are present on those edges. But perovskite, those halide perovskite, which is present inside the perovskite solar cell, it is a special type of synthetic perovskite. And this is the basically, halide perovskite is derived from the basically same perovskite, but halide perovskite, those A side cation are either organic cation, methyl ammonium, formamidinium, or cesium, or B side cation are either lead or tin, and all the anions are halide. And very basic example of halide perovskite present in perovskite solar cell is MAPI, which is very, very popular, MAPBI3. By changing A side component, B side component, and X side component in the same way, this is the A side cation, and this is B side cation, those are anions. By changing their composition, we can make a library of perovskite. And those different perovskite, they have different importance. And those perovskite having lower band gap and perovskite having wider band gap, they are very, very important to make multi-junction devices. And often in this presentation, we'll encounter word band gap. And what is band gap? Band gap is simply the difference between valence band and conduction band. And in methyl ammonium lead iodide, the difference between valence band and conduction band is 1.55 electron volt. That is the band gap energy. In perovskite solar cell, those perovskite material, this perovskite material is sandwiched between other two auxiliary layers. Those two auxiliary layers are their charge transport layer. Yeah, whenever perovskite, in presence of light, it generates positive and negative charge. It generates positive and negative charge, and those charge transfer layer separate the charge. And how does perovskite solar cell work? I think I need to go direct HDMI. Let's see. Stop. Let's see. Yeah, that's just some problem. Let's assume this is a perovskite, and there is valence band and somewhere conduction band. And whenever perovskite absorb light means perovskite absorb light, which is equal to the band gap or greater than the band gap. The difference between conduction band and valence band is band gap. And whenever perovskite absorb light equal to or greater than the band gap, it will generate charge, positive and negative charge. Simply negative charge is electron and positive charge is hole, whatever is left over. In absence of other auxiliary layer, those electron and hole, they recombine, their life is very short. But in perovskite solar cell, there are other two layers to separate those charge. One layer is electron transport layer. It selectively separates photogenerated electron from the perovskite. It selectively extract negative electron. There is another layer which is called hole transport layer. It selectively extract positive charge, that means a hole from the perovskite. That means HTL and ETL help to separate the electron. And finally, those electron and positive and negative charge are collected towards two respective electrode, and we can get electricity. And what are these electron transport layer and hole transport layer? Electron transport layer, simply, it is the N-type semiconductor which selectively take electron from the perovskite, photogenerated electron from the perovskite. And hole transport layer are P-type semiconductor. They selectively extract positive charge from the perovskite. Based on the direction of hole transport layer and electron transport layer, perovskite solar cell are divided into two types. In the first type, if you look at here, the direction of the light, if light passes to the perovskite solar cell through electron transport layer, that is N-type semiconductor, and after that perovskite comes and P-type semiconductor. If you read NIP, this is the NIP structure. And previously, this structure was incredibly popular. The reason most of the high efficient perovskite solar cell used to be NIP. However, there is some problem. The fabrication process of this type of structure is complicated. The reason it contains those metal oxide electron transport layer as a bottom, and we need to heat it to high temperature for longer time. And as well as the whole transport layer present in those NIP architecture for efficient devices is pyro-emitted. This is the organic compound. In pure form, its performance is very low. That's why to make it work, we need to add some additive, and those additive make solar cell unstable. That's why people slowly started to focus on the PIN architecture. PIN architecture largely solve the problem associated with NIP architecture. The reason here, people deposit another organic electron transport layer directly on the top of the perovskite. It does not need any additive to function. But however, it solves the problem partially, but this organic C60, it has a bunch of other problems. NIP architecture, it is important for the commercialization, and it is more stable as compared to PIN, and also it is more compatible to the multi-junction devices. However, the electron transport layer which goes to the top of the PIN architecture is very, very limited. It is limited to C60. And this C60 has several problems. The first problem is, in solar cell should have higher stability. But if you compare the stability of perovskite solar cell as compared to the silicon solar cell, the stability of perovskite solar cell is very low as compared to silicon. That is due to C60. That means C60 is fragile whenever it comes in contact with stress, external stress, such as high temperature or mechanical stability bending. It starts showing crack, and also it starts showing fracture. And also, C60 is very, very expensive. It has very complicated fabrication process, and due to complicated fabrication process, it is expensive. And also, for the solar cell, and we need mass production, and mass production is very, very difficult. And we cannot deposit C60 by solution phase, and we need to use a special type of deposition technique. This is vapor deposition, and which is expensive. And how big is the problem C60 is? This is published in recent paper, and in their stability test, stress test, and always C60 is the first layer which peels off, and that causes damage of the solar cell. That's why to extend the life of perovskite solar cell, and then to reduce the cost of perovskite solar cell, we need to find alternative of the C60. And there are some other alternative of C60. those are metal oxide. However, metal oxide, they are inexpensive. They are also scalable. We can deposit metal oxide by solution phase deposition, and as well as metal oxide has high stability, but due to their difficult processing condition, those metal oxide are suitable as a bottom layer. Inorganic electron transport material have several benefits, and they are scalable, they are more stable, and they are inexpensive. However, all inorganic electron transport layer material, they are not equally ideal. People started using titanium dioxide during the development of perovskite solar cell. The reason it was borrowed from the dye-sensitized solar cell, but it has some problem and it needs high temperature processing. That's why the use of titanium dioxide is very limited, and we cannot use it for the flexible substrate. The plastic-based flexible substrate, the melting temperature is above 120 degrees Celsius. And also, titanium dioxide undergoes photocatalytic reaction in presence of UV radiation, and which causes degradation of the perovskite as a whole. And after that, to solve, people started using zinc oxide, and zinc oxide has some useful property, and we can process zinc oxide at low temperature, and also it has high charge mobility. But zinc oxide, it is alkaline in nature, basic in nature. Due to basic nature, it reacts with perovskite and also causes degradation. And after that, people started using tin oxide. And tin oxide largely solved the problem related with titanium dioxide and zinc oxide, and we can process it at low temperature, and also it has high charge mobility, and also it has higher stability. And more people started to work on tin oxide. And here, those all are the useful property of tin oxide. That's why tin oxide is so popular. And if you look at the chart here, we can see the popularity of tin oxide. The power conversion efficiency of the tin oxide-based device increased over a year, and already the power conversion efficiency already surpassed 20. Yeah, it's a little bit older data, 25%. It's about, and already surpassed 26%. And however, the problem with tin oxide, it has so wonderful property, but the problem of tin oxide, it is also metal oxide. Problem, it is also suitable. It is only suitable to deposit as a bottom layer. Can we deposit tin oxide directly on the top of the perovskite, and then we can give alternative to C60? People deposit C60 on the top of the perovskite. Can we use tin oxide? Can we replace C60 with the tin oxide? There are two fundamental problems to deposit tin oxide directly on the top of the perovskite. Perovskite material, they are sensitive. It undergoes degradation in presence of high temperature and in presence of polar solvent. And tin oxide dispersion is stable in water, and we cannot deposit any water-based solution on the perovskite. It undergoes degradation. And another problem, and if we heat it to perovskite higher temperature, it also undergoes degradation. That's why, here we can see, and when a perovskite comes in contact with water, it undergoes degradation. And another way we can deposit metal oxide directly on the top of the perovskite is depositing precursor and heating to high temperature. And if we heat perovskite to high temperature, it also undergoes degradation. That's why to deposit tin oxide directly on the top of the perovskite, we need pre-synthesized tin oxide in perovskite compatible solvent, and which is very challenging job. And the main aim of this work is to solve this problem and to make tin oxide compatible with perovskite and to deposit directly on the top of the perovskite. That's why on the next section, I'll be talking about how can we make tin oxide compatible with perovskite, and how can we deposit tin oxide directly on the top of the perovskite, and we can give better alternative to C60. From our previous discussion, to deposit metal oxide directly on the top of the perovskite, we need pre-synthesized metal oxide. And for this, I synthesized tin oxide by neutralizing tin salt with a base. And this is the tin oxide powder. The name is hydrous tin oxide. This tin oxide was dried at room temperature. That means metal oxide, which was dried at normal condition, still it contains a lot of areas of water. That's why it's hydrous tin oxide. And I tried to make a stable dispersion of tin oxide in perovskite compatible solvent using hydrous tin oxide, but I was never able. That never worked. And after that, I selected the second route to bind tin oxide to attach some ligand, to attach some extra group on the tin oxide. And after that, I selected carboxylate as a proper group. And after that, and I mix tin oxide with carboxylic acid and heat it to high temperature. And whenever I heat it, and finally I got a clear solution of tin oxide. And this tin oxide contains carboxylic acid, carboxylate attached on the tin oxide. That's why from powder, and we are able to get the clear solution. But still, we don't know. There is still tin oxide. And to identify there is still tin oxide, we characterize this tin oxide using normal characterization technique, XRD and IR. And if you look at the XRD diffraction pattern, the peak position of the tin oxide before and after functionalization, before and after, that means the tin oxide, the XRD diffraction pattern of this solution tin oxide and the powder tin oxide, the peak are aligned with each other. That's why we can say, and after functionalization, still this clear solution can be in the tin oxide phase. But it does not tell all the story, and after that we characterize it using IR. And here the peak, which is present around 650. This peak related to tin and oxygen bond in tin oxide. And after functionalization and in this clear tin oxide solution, there is no change in peak position, and we can say, and this clear tin oxide has still this has the same tin oxide present here, but the form is different. And after that, we try to find the stability of this tin oxide solution in different perovskite compatible solvent. This tin oxide likes lower alcohol, and we can make very stable solution up to butanol, and also it likes other polar solvent. But here we are more interested with lower alcohol, and which is perovskite compatible. And for our initial testing, we selected ethanol as a test solvent, and after that we diluted tin oxide in ethanol. And after that, we deposited this tin oxide dispersion in ethanol directly on the top of the perovskite. And this is the schematic of the deposition. And here it shows that is the fully converted perovskite. And after tin oxide deposition, the color has changed to shining color due to reflection. Here, we make tin oxide, and then we functionalize it, and after that we diluted it. After that we deposited it on the perovskite. But we don't know, is it still perovskite compatible, or it caused degradation to the perovskite. To identify it is still perovskite compatible, we characterize it using common characterization technique. If you look at here, this is the scanning electron microscopic image of this perovskite, fully converted perovskite, and we can see perovskite grain. After tin oxide deposition, still we can see perovskite grain, but those are less visible. That is due to the reason there is presence of another extra layer here. That's why those are less visible. And after that, we characterize it using X-ray diffraction. This is the X-ray diffraction pattern of the perovskite. This perovskite before tin oxide deposition. This is the after tin oxide deposition. This peak, which is presented 14.2. This is the signature peak of the perovskite. And after tin oxide deposition, there is no change in perovskite position, and also those peaks are exactly aligned with each other. And here we can say still after the tin oxide deposition, the perovskite is still in the perovskite phase. And also another thing, whenever this perovskite undergoes degradation, it makes lead iodide. And if we do XRD of the lead iodide, it gives peak of the lead iodide in between around 12. And there is no any peak present in around 12, and there is no any peak below 14.2. That means this tin oxide is not causing any degradation of the perovskite. That's why it is perovskite compatible. To verify again, we did UV-Vis analysis, and this is the UV-Vis absorption pattern of the perovskite before and after the tin oxide deposition. And those peaks are completely overlapping with each other. That's why it shows this tin oxide dispersion is completely perovskite compatible. And based on this result, we fabricated perovskite solar cell. We deposited tin oxide directly on the top of the perovskite. And this is the digital photo of the solar cell we made. And after that, we divided it into a small pixel. And after that, we measure the power conversion efficiency of the pixel. And this is the cross-sectional area. We break this solar cell, and after that, we took a cross-sectional image using SCM scanning electron microscopic, and this shows an all the layer present. This is the ITU, this is the PTA whole transport layer, and this is the perovskite layer, and also this is tin oxide layer. It shows all the layer. And after that, we measure the power conversion efficiency, and we are able to get power conversion efficiency up to 14%. And this work, it's a simple, but it's a fundamental. The reason people never did made cell before depositing tin oxide directly, metal oxide directly on the top of the perovskite solution phase. People can use other method, ALD, but ALD is super slow, and this is not, this does not have any practical application. And this is the demonstration of first practical application. We can deposit metal oxide directly, solution phase metal oxide, and we can make functional perovskite solar cell. And also, we make a control device depositing C60, which is the benchmark electron transport layer for PIN architecture. And for the control, we got 15.1% efficiency. And this efficiency for the tin oxide device is not that much far away. That means, here for the first time, we successfully fabricated perovskite solar cell, depositing solution phase tin oxide directly on the top of the perovskite. And what is the significance of this work? First ever we fabricated perovskite solar cell depositing metal oxide directly, and that work nobody did this work. It was completely new concept, and after that we patented it, and that work helped us to start a company startup, SOFAB, and also from the same concept we were able to secure first phase of the America-made perovskite startup prize, and which was the foundation of our startup company, SOFAB. And on the next step, I'll be talking about flexible perovskite solar cell. Here, the reason flexible perovskite solar cell has several applications, and perovskite solar cell, we can make lightweight perovskite solar cell having high efficiency, and solar cell with lightweight solar cell with high efficiency has potential application in several fields, such as integration into building, vehicle, aviation, and also recreation, and also we can make it, we can use it for the wearable electronics. However, the fabrication of flexible perovskite solar cell is a little bit challenging. The reason, to make it expensive, we need to use expensive substrate, that is a plastic-based substrate. But plastic-based substrate, we cannot heat it to high temperature. It undergoes deformation, it will melt. That's why main precaution here, we need to design something which we can process at low temperature. That's why we already designed tin oxide, which we can process at low temperature. And after that, we fabricated flexible perovskite solar cell, and we tried to translate exactly same thing. What did I do previously on the plastic? This is our schematic. This is the roll of plastic. We clean it, and after that, the same way we deposit all the layer. We deposited HTL, perovskite, and ETL from blade coating. And here, it contains stack. It has HTL deposited by blade coating, and also perovskite deposited by blade coating, and also it has ETL tin oxide. We deposit tin oxide directly on the top of the perovskite. And after metal deposition, and we made a flexible perovskite solar cell. And after that, we measure power conversion efficiency, and we were able to get power conversion efficiency up to 14.5%. At that time, still this power conversion efficiency 14.5% on the plastic-based substrate. Yeah, it was very good. But if we compare it with glass-based substrate, and it is still less. But on the next section, I'll be talking about how can we improve the power conversion efficiency of the flexible, or like the power conversion efficiency of the flexible perovskite solar cell. The tin oxide here we use, it is low temperature processed, and to make metal oxide efficient, we need to heat it to high temperature. But however, we can improve the performance of low temperature process tin oxide using different modifications. The first approach people use is elemental doping, and here we also use the same strategy. we went through literature, and then from the literature survey, we found a couple of elements which we can use to mix with tin oxide. And after that, and based on the literature, we found yttrium is a suitable candidate. There are more literature, and also yttrium is not going to change color of the tin oxide. And after that, we synthesize yttrium doped tin oxide, and also we functionalize it with acetic acid, that means acetate, and finally we diluted this tin oxide. And we made a series of flexible perovskite solar cell depositing yttrium doped tin oxide, and here we made yttrium doped tin oxide ranging concentration 0 mole to 3 mole. And this is the box plot which summarizes the power conversion performance of the flexible solar cell fabricated by depositing yttrium doped tin oxide directly on the top of the perovskite. If you look at here, we got higher power conversion efficiency from the tin oxide, which contains 2% yttrium. Basically, the improvement in power conversion efficiency is coming from improvement in VOC and improvement in fill factor. And if we compare it with undoped tin oxide, that is the pure tin oxide. It does not have yttrium. And tin oxide without yttrium, we are able to get 14.3% efficiency. But whenever we incorporate 2 mole percent of the yttrium, we are able to get 16.5%. That is huge improvement. So we got improvement by 2%. But however, the performance of perovskite solar cell, it also depends on type of perovskite composition. Previously, we understood we can make various perovskite composition by changing S side, B side, and X side component. And here I'll be talking about how can we improve the performance by changing perovskite composition. Initially, during the development of perovskite solar cell, people were using just single cation perovskite, Ma based, that is MaPbI3. And however, the performance improvement of MaPbI3 based perovskite solar cell is very limited due to its properties. And after that, people slowly started to using another different type of perovskite composition, basically formamidinium based. But formamidinium based perovskite pure, it is very unstable. That's why all of the perovskite here people use, it is the mixture of more than one type of cation. That's why to make this stable. And if we mix some other component on the perovskite and make different either mixed cation or triple cation, and we can get improved properties. That means we can get improved stability. Also, we can get higher efficiency. And in the same way, we selected 4 different types of perovskite based on their properties. And the first, people are using MaPbI3, also we use the same perovskite. And after that, we went to mixed cation perovskite. Mixed cation perovskite has more higher tolerance towards temperature. And after that, this is also mixed cation. And after that, we make triple cation. And triple cation, it contains cesium. It increased the tolerance towards humidity, and also formamidinium increased the tolerance towards high temperature. And based on the property, we selected 4 different types of perovskite, and depositing tin oxide directly on the top of the perovskite, we make perovskite solar cell. And when we changed the perovskite composition, and we were able to get power conversion efficiency up to 20%. And this is very incredible for the flexible perovskite solar cell. And if you look at here, the power conversion efficiency for triple cation based perovskite is the highest as compared to other. And here, if you look at here, triple cation contains more than one cation. How many? 1 cation, 2 cation, 3 cation, and also it contains 2 halide. Here, if we add cesium cesium increase the stability towards humidity. And also formamidinium will increase the stability towards moisture. And if we add both cesium and formamidinium on the methyl ammonium, and we can get perovskite with superior quality. That is due to improvement in quality of the perovskite, and we are able to get much higher power conversion efficiency as compared to other perovskite composition. So MAP means MaPbI3 and mixed cation, this composition, and we have different composition. It's like That's why in this section, by elemental doping on the tin oxide, and we were able to increase the power conversion efficiency from 14% to 16%. And after that, on the second step, we changed the perovskite composition. By changing perovskite composition, and we were able to get power conversion efficiency up to 20%, and which is incredible for the flexible perovskite solar cell. It is on the large area. And next section, this is my last section, and I'll be talking about multi-junction devices and what is the benefit of perovskite. Yeah, this is the same curve we looked at earlier. Here, if you look at this, the progress in power conversion efficiency of silicon-based solar cell, yeah, almost the progress in power conversion efficiency is flat. The reason, it is already reaching to the maximum, yeah, it is already reaching to the practical limit. And how much power conversion efficiency we can get from different photovoltaic technology, we can get idea from here. Silicon solar cell, we can get highest theoretical power conversion efficiency up to 31-32%. But that is the theoretical. But how much maximum we can get experimental, there are a lot of loss. That's why we are already more than 26%, and we are reaching to experimental limit. That's why the way to increase the power conversion efficiency is to make the multi-junction device. This is the silicon solar cell. We can fabricate perovskite solar cell on the top of the silicon solar cell, and we can get higher power conversion efficiency. How does multi-junction device work? Let's say in single junction, let's assume perovskite solar cell. It is a single junction solar cell, and light has a wide spectrum, wide range of radiation, short wavelength radiation to long wavelength radiation. Perovskite can effectively manage, effectively convert this short wavelength radiation into electricity. And silicon solar cell, it can effectively utilize those long wavelength radiation, that means from the red region. If we stack perovskite solar cell on the top of the silicon solar cell, and we can do better light management, and then we can utilize wide range of radiation, and we can get higher power conversion efficiency. That's why to make a multi-junction device with silicon solar cell, we need wider bandgap perovskite. And how does the tin oxide, that new material we fabricate, works with a wider bandgap perovskite? And after that, yeah, to make silicon perovskite tandem devices, the first step is to we need to design wider bandgap perovskite. And here we design wider bandgap perovskite with this composition and bandgap up to 1.69 electron volt, and that is suitable to make perovskite silicon tandem devices. And here, we deposited tin oxide directly on the top of the perovskite and make device, and we were able to get power conversion efficiency up to 17% with incredibly high open circuit voltage. That's why from here we can say the new material which we develop here, it is highly compatible with perovskite, and it can be the substituent of C60, which is the problematic for the commercialization perovskite photovoltaic. And yeah, that is our team at SOFAB. Then we started SOFAB around 2022 when we got award from DOE, and the basis for the award was first part of the work, and this is our team, and this is the photo when we win award, and Dr. Gab Rouse and Dr. Thad Raffel on advisory board. And thank you very much for my advisors and for collaborator in chemistry department, Josh Pack family. And thank you very much. Yeah, if you have any question, welcome. It's a very technical. I try to explain in a simple way.
What do you mean by percent self-efficiency?
Yeah, that's one thing. Like solar cell, people say in silicon solar cell in market, oh, there's different type of solar panel, and whenever they sell the solar panel to people, and they say, oh yeah, we are selling silicon solar cell with that much power conversion efficiency. That means this is the efficiency that can convert that percentage of solar energy into electrical energy. Yeah, that is the benchmark of the solar cell.
So a practical question.
Sure.
Since you're right on the leading edge with the research, obviously you patent and you publish a lot. But the processes, some of them I assume that you keep as a trade secret. Where do you draw the line?
Yeah, there is one thing. Yeah, oh yeah, exactly. It's a very good question. Yeah, this is our general process, but there are other secondary process in which we need to make those tin oxide, and those things are secret. And then most of the time, yeah, my friend Peter works on this stuff, and yeah, he knows those secret. And we need to optimize a lot of things, and this is difficult for people to translate. Yeah, those are not published.
Thank you.
So, when I hear talks like this, a key concept is always the efficiency of the
Yes.
cell. I wonder if it's maybe not overemphasized. I remember hearing once that the amount of sun energy that strikes the
Yes.
Earth in a day is very large compared to total energy consumption over a much longer period of time
Yes.
on the planet. So maybe what's more important is that you can make a lot of this stuff cheaply.
Yeah, but there is one thing is a problem. A lot of stuff that the main cost goes to installation and packing. And if you can make more efficient solar cell, if you can make a multi-junction solar cell, and we can reduce cost on the insulation and installation.
Do you ever do the calculation of
Yeah.
how much of this stuff you need to make to power the Earth? So
Yeah, that's a good question. Thank you for the question.
do that, please write me an email.
First, congratulations again on winning the award. Nice talk.
Yeah, thank you very
I
much.
have a technical question. if it's
Sure.
okay. When you dope the tin oxide, do you know where the location of the dopants are?
Yeah, thank you very much for the question. It's a very good question. And here we try to identify. We sent our sample to expertise in national lab, and their conclusion was still the amount of yttrium what you are incorporating is very low. That we can show there is a presence of yttrium, but we are not sure is it actually inside the crystal lattice or it is in the mixed form. Yeah, we try to verify this several times.
Just as a quick follow-up, what is the tolerance for perovskite structure to incorporate, this type of dopant inside the crystal?
Yeah, yes, very good question. But here from our study and those yttrium, there might be a problem if we dope with other cation like lithium, and that goes and interact with perovskite. But we didn't find any interaction of yttrium with perovskite. I think it is pretty stable inside the tin oxide lattice. Yeah, most of our testing company people in other university partners too, and yeah, as far as we remember, and we do not encounter such type of problem.
What are these tin oxides? These are spherical particles, tin oxide, and you make those?
Thank you. It's a good question. Those tin oxide nanoparticles, yeah, they are spherical particle, and then
What size?
yeah, based on the measurement last time, yeah, Peter verified it. They were sub 5 nanometer.
Oh, less than 5 nanometers?
Yeah, less than 5 nanometer. Yeah, Peter, I'm making.
We buy Saks and TM, we got 3 nanometers.
Yeah, 3 nanometers, 5
Is
nanometers.
that important, the size actually?
Yeah, that is important one for the exactly for the packing. If you have a small nanoparticle in it, yeah, you have better idea than me. And they always if you have a small particle, they always make compact film. Yeah, see, film compactness is yeah.
I have two totally trivial questions. One, when you showed the printed product, it's a solar cell on top, but it looked like a very inefficient postal worker put stamps on
Okay. Gotcha.
All over in a regular array, but all over with a lot of space in between. No, it was actually a printout
Okay.
there.
Yeah.
Which is the solar cell? Is that whole thing the solar cell, or is it just the little
Yeah,
squares?
the whole thing is solar cell and the smaller pixels. Yeah, we measure efficiency of the pixel. The reason there are a lot of empty space, this is just our lab research. That's why we do not care much about the.
No, I didn't know if this was.
Yeah.
But that whole thing would be an array that would go on the surface of a cell.
Yes. Yeah, this whole whole thing, it goes to the surface. Those are small individual pixels, 0.25 centimeters square, and we measure efficiency of each and every pixel. But it goes as a whole, it goes to solar cell.
The other thing, I've never seen a bar graph that has an arc on the right side with little things in between. What is that? What's? I mean, I couldn't make out any of the writing.
Yeah, which?
Your box plot with the distribution.
Okay. Yeah, I have two box plot, I think. Yeah.
Yeah,
Oh yeah.
Those.
Yeah.
What is that? I mean, what's the thing on the side?
In this side. Sorry.
Yeah, there's an arc. You're a bulb.
Oh yeah. Yeah, that is the distribution and how. Yeah. Let's say this is the. It's an open circuit voltage. This is the open circuit voltage of the different pixel, and here we measure. Those dot are different pixels. Yeah, exactly the same way you were
Those are
asking.
the actual data.
Yeah, actual data.
Those are the data points. And then how
Yes.
does that get converted into the rectangle? Is that rectangle?
Yeah, this rectangle based on the data it calculate. It's a percentile and where is the mean, median, and everything. Yeah, based on the data it calculate. It's a statistics. Yeah, we calculated it using Origin software and it calculated itself.
On that photograph you showed, each of those little squares.
Yeah, those are its
you're
pixel.
getting the data point
Yeah.
at each of those different squares.
Yes.
Since the array of pixel cells was brought up, how much variability do you have across?
Yeah, it's a good question. Definitely there is some variability. The reason
Oh,
here we make
obviously,
small scale, and yeah, whenever we do blade coating, and always the concentration is higher at the beginning, and if you go further and further, and due to fast nucleation at the beginning, and then we'll get lesser and lesser deposition, like thin film at the end. There is some variation. That's why we need to always take average.
So
And-
you have steps in SOFAB
Yes.
where you're trying to produce all?
Yes, but no. If we make larger area device with continuous supply of ink, yeah, we are not going to see variable. That's just blade coating. We inject solution, and after that we do blade coating. The solid which is present is not infinite. This is limited. Yeah, and over time that will lose the concentration, and less concentration, less nucleation, a thinner film.
I just want to add a comment and give a little more credit to Sashil than what he's claiming for himself. So he was able to get up to over 20%. And for these types of cells, you know, the top of the line is 26 point something now.
It's for the flexible, it's around 23.
Yeah. Okay, Ron, he is working under conditions focused on scalability, right? So using materials and methods that you could actually use on an industrial scale. Most of these champion devices that you'll see in the literature or are, what are the sizes?
Yeah,
there?
it's
0.1 centimeter square?
yeah, it's smaller than.
Smaller than 0.1 centimeter squared, and it's made on a spin coater,
Yeah.
which gives you a very uniform distribution, but there's no way to actually scale this up to manufacturing. And so every time he goes to publish a paper, we get a reviewer who gets hung up that we're not at state of the art. But we're not trying to go from 26.1 to make it 26.2. Sashil's trying to make something that you could actually manufacture on a large scale and have a practical device. So I think he didn't make that point, so you may look at his numbers and say, oh, he's 5% away from state of the art. No, this is, for what he's doing, this is state of the art.
Yeah, thank you very much. Thank you.
And then I'll ask one question.
Sure.
What is your product that you sell? I mean, not like all the nitty-gritty details, but what is your company doing? What are you selling?
Yeah, basically we are selling the same yttrium doped tin oxide, but we have another product. We
But
recently made.
you're selling the solution?
Yeah, we are selling this concentrated solution.
And how stable is it?
Oh, it's stable for years. Yeah, it's still, yeah, we made at the starting of the 2020. Still, those are sitting in lab. They're stable.
Any other questions?
Thank you very much, Cecile. Much for people to think of at all the different levels, from the undergraduate, graduate, postdoc, on the faculty members. And we'd like to congratulate you again for your outstanding accomplishments, the George Pack Award. And very much thank the family members for coming in and their ongoing support.
Yeah, thank you very much.